Hello, my name is Tavis Ormandy. This is Julien Tinnes. We're information security engineers on the Google security team. And our talk is called There's a Party at Ring 0, and you're invited. So, all systems make assumptions about kernel security, and in fact, the entire security model of some systems can be based on the security boundary provided by the kernel. Things like sandboxing in Google Chrome and Android make Google in particular dependent on kernel security. And of course, this is true for lots of other applications on other platforms. So we've been involved in finding, fixing, and mitigating some really interesting kernel bugs over the last year, and we're going to share some of our work today. So we're going to discuss some of the ways that you can protect the kernel from malicious userland code and mitigate unknown kernel vulnerabilities that in the kernel itself. So the first section of our talk is called The Kernel as a Target.
So imagine you have arbitrary code execution on a machine, and if you want to escalate or just merely switch your privileges, because it's not necessarily an escalation, you might want to get the privileges of just another user. What can you target? You can target, in general, processes with more or different privileges. So for instance, running daemons, SatuID binaries you can execute on Unix. And you can also target the kernel. And the kernel has a lot of nice properties for you as an attacker. For instance, it has a huge code base. It performs a lot of complex and error-prone tasks. And it's responsible for the whole security model of the system. So it's really a primary target for you. The Linux kernel has been a local target for over a decade. We've seen many different kinds of bugs. We've seen memory and memory management corruption type of bug, which is the first type of bug versus logic bugs. And the complexity of a kernel makes for more diverse and interesting logic bugs than in userland usually. We've listed here a few logic bugs that we really liked. In particular, the first one I think is a really good example of things going wrong. So if you want to take a look at this, they are really interesting. And we've seen also memory management corruption bugs. And they also tend to be more interesting and diverse than their userland counterpart, where it's almost always the same. This is due to, first, the complexity of the memory management, because of course the kernel is handling the whole memory management. And it's also due to an interesting different paradigm where the attacker actually finally controls a full address space. So this allows an attacker to make way more complex attacks because he had the control of a whole address space to finally exploit any bugs he might find. On the other hand, in userland, usually if you're trying to exploit a bug remotely, trying to get control over the address space by itself is already something quite hard, and that's why you see things such as heap spraying and all those things. They are just giving you some control over the address space. In this paradigm, you have full control. So we've also listed a few bugs that we won't detail today at which you can look if you're interested. We will just mention today the null or two userland pointer dereferences. We will mention two of those today and give them as example. So escapes through the kernel. And exploiting the kernel is often the easiest way out of basically all kind of sandboxing techniques. So old school ones such as ch-root jails, which have been used forever, mandatory access control, which has been gaining traction in Linux for the last 10 years, but is still not really widely used. Container style segregation such as vserver. And I'm only talking about Linux right now, but on Windows you see the same thing happening. Using those for segregation, you still mostly exploit the full kernel attack surface. which is also why virtualization is a popular alternative, because it gives you a very different security. Because you have, as an attacker, you will have to attack the virtualization layer instead of just having to attack a kernel to get out of a CH-root jail or any traditional sandbox. And things such as mandatory access control, for instance, SE Linux, they make more sense if you have a fully featured security patch, such as GR security, that also tries to protect the kernel. In Windows, the situation has been different, but it's getting more and more the same. Traditionally, local kernel bugs were not considered really relevant and important on Windows. It has changed somewhat recently, especially since the introduction of Windows Vista. And we can see an increased reliance on domain control, the use of network services, and features such as protected mode and integrity levels have been introduced with Windows Vista. So this has changed in the last few years, and now Windows is roughly in the same situation as Linux now, and people care more and more about local privilege escalation on this platform. So it's a bit of the same. There's still no real big complex mandatory access control system on Windows, but that's the biggest difference now. In terms of remotely exploitable bugs. On Linux, they have been quite rare. We have seen a few notable exceptions around 2004, 2005, when Wi-Fi was getting more and more used and was getting into the Linux kernels. We've seen a few remote exploits by different people. But otherwise, there is this rare exception, SG RACU SCTP exploit, which has been released, I think, 2 years ago. He has written a really interesting article in Frac if you want to check this out with Twiz, and a few others, but it's not very common. On Windows, they have been quite popular for at least 6-7 years. I think actually Barnaby Jack, who gave a talk yesterday, gave a talk in 2005 on some remote kernel bugs on Windows, and usually the target was not Microsoft code itself, but mostly third-party naive code in antivirus and personal firewall. You've seen also a few GDI-related bugs, very few TCP/IP stack-related ones. Our colleague Neil Mehta and others have found one quite recently. Also, you've maybe noticed this SMB v2 exploit by Immunity last year, which generated some buzz and was quite impressive. So those were nice remote kernel bugs. But the web browser are really what are changing the game now, because surprisingly, they do expose kernel attack surface remotely. For instance, through GDI. And it's something that we've also seen on Linux. For instance, there has been a remotely exploitable bug in NVIDIA drivers that you could actually exploit through a web browser. And the reason for that, and Tavis will talk a little bit more about it later, is that we have tons of new features coming to the browser, such as web font, WebGL, and so this exposes a lot of kernel attack surface remotely. So we will now present some of the bugs we found this past year.
So we were working on kernel security for about a year, and over that time we published lots of bugs, and we've still got some that are unpatched. We're still waiting for fixes for some of these, but yeah, we found quite a few over the course of this year. So there are many entry points for an attacker to reach kernel attack surface. The obvious ones are system calls, but there's also things like ioctls, anything that the kernel passes. File systems weren't traditionally considered part of the kernel attack surface, but in recent years with things like AutoMounter, it's a legitimate way to attack the kernel. Obviously, there's things like network protocols which are extremely attractive to attackers, and primarily on Windows you have things like fonts and other formats that are handled in kernel. Of course, there's been lots of issues with executable formats, which are quite complex object formats. on Windows and Linux. There's been famous bugs in Cough, ELF, A.out, and so on. But one underappreciated entry point that we considered were DPL3 interrupt handlers. So we decided that we should take a look at this stuff. So we found one interesting issue on Windows 2003. So Microsoft introduced a new DPL3 IDT entry. DPL3 just means accessible to ring3 code. So in the public symbols, Microsoft called this KI raise assertion. This basically makes if you execute into C, it makes it roughly equivalent to just raise exception status assertion failed. So this is kind of odd. I've looked at lots of Microsoft code and I've never seen them use this feature. And in fact, looking at the implementation in the kernel, it turns out that they made an interesting error. They dispatched the interrupt before enabling. They dispatched the exception before enabling interrupt. So this bug, while not particularly high impact, it had two interesting characteristics. The exploit, you simply just invalidate the ESP and then call int2c, so you could exploit it in just 4 bytes. And the patch was interesting as well, simply because they had to just re-enable the interrupt flag, so that's just 1 byte instruction, STI. So it's not particularly high impact, but we thought it was fun because of this, and I actually have a video of it of this happening. Okay. Oh, okay. So I'm just using CDB to open an executable so that I can patch some code into it. So yeah, I just choose any random executable so that I can use the assemble function from the Windows debuggers. So yeah, just invalidate ESP. Call int2c to raise the exception. Detach from the process. And yeah, you see, soft dice detects the fault and it breaks due to fatal. If I turn off faults and then let it continue, you get a bug check. So it's kind of a funny bug. But this one wasn't particularly high impact, but it was just interesting and shows that really there isn't much exploration from researchers in this area. Let's see. Okay, so on the subject of exceptions and interrupt handlers, a recap of how page faults work. So as I'm sure everyone knows, a page fault occurs when there's some attempt to access a non-present page. But it's also if you have insufficient access to touch a present page, and there's various other low-level paging related errors. So when a page fault occurs, the page fault, the handler of a page fault is passed an exception code, which has a number of flags that describe what happened when the page fault occurred. So the flags are ID, which explains whether the page fault was caused by an instruction or data fetch. US, which means the page fault occurred during user or supervisor mode. WR, which says whether it was a read or write, and P or NP, which means present or not present. So, supervisor mode, which is what sets the US bit, is set when the page fault occurred during some privileged operation. So if the supervisor bit is set, it can mean various things. It could mean that a kernel bug was encountered, and then you'd expect to see an oops or a bug check on Linux or a bug check on Windows, or some other kind of panic. But it can also mean some other unusual low-level event happened. You'd expect it would be normal for that to occur during something like a copy from user operation. But in most other circumstances, it would mean something unusual happened. By looking at this code, we realized that if the processor can be tricked into setting these flags incorrectly, then you can confuse a lot of really privileged core operating system code. And so we were thinking about this for a while. And we came up with a way to do this. What we did was study the machine state of while executing a virtual 8086 mode task in VMware, in a VMware guest. And we actually found a way to make VMware set the supervisor bit for an unprivileged page fault. So the problem was, if you do a far call in virtual 8086 mode, it was emulated incorrectly. So obviously when you get a far call, you'd expect that the CS and IP pair to be pushed onto the stack. And this is actually done with supervisor access. It's reasonable to understand why VMware did this. They were probably trying to reuse their real mode emulation code for if you wanted a DOS guest or something like that. It's obviously pretty reasonable to use supervisor access for that because it makes no difference. But in virtual 886 mode, Intel actually guarantees that you're always running as ring3. It's as a CPL3. It's very clear in all of the manuals that this is guaranteed. So this was an error. And surprisingly, we were able to exploit this, get ring0 code execution in a VMware guest. The reason we were able to do this was because the Linux kernel has a magic check, has a check for a magic CS value to look for an unusual event caused by PNP BIOS support. But because this magic value was something that you wouldn't normally be able to set, in virtual 86 mode you must be allowed to set it because this is how real mode addressing works. Obviously addresses are 16 bits in real mode, but the address space is 20 bits. So you do this by shifting around CS and adding it to IP. So in order to access the full 20-bit address space, you need to be able to set any CS value. Obviously, this has a special meaning in protected mode, but in real mode, yeah, it doesn't mean anything. It's just part of the address calculation to form a physical address from an address. So believe it or not, we can actually exploit this error. It might be surprising, but we worked on this and we actually got it to work. So all we have to do is mmap our shellcode at null, and then we enter VM86 mode. So as when we were working on this, there was a new feature that was beginning to gain popularity called mmap min adra. At the moment, it's quite well known and well used, but at the time we were concerned that maybe people would say this issue wasn't really realistic because of mmap min adra had just been introduced. So we found a way to bypass that as well that we're going to talk about later. All we had to do was set up a file call to a non-present page at SS when a non-present page was at the SSSP address. A PF is delivered, which is as expected, but because we can set these magic values in CS, and then which is recognized as a PNP BIOS fault, then because the kernel wasn't expecting this fault and there was no handler set up, the fault handler isn't installed. It's a BSS object, so it's set to null, and the kernel just jumps to null, and then you've rooted the machine. So this is how we triggered it. We basically you set some nonsense in ESP and SS so that you'll cause a page fault because obviously this page isn't going to be present. Then we set CS to 90, which is the magic value for PNP BIOS faults. And then we did this file call, and that was it. Basically, the kernel would just jump to our code as at ring0. So this was one of the first issues we found with page faults, but we found some more as well on Windows. So obviously, it's well known that if the kernel ever trusts any data from user space, then there's going to be a security issue somewhere. But it's not just the presence of data that users control; it's also the presence or absence of data. So you can set up some nonsense and tell the kernel this is like some data structure is expecting, or you can say there's more data here than was expected, or less data than expected, and strange things can happen. So by claiming we have more data available than we really do, then we can reach lots of unusual error paths. This is mainly true on Windows because the main system types are large interdependent structures that often have multiple components, and they sometimes have version numbers where you have to read the version number first to see how big the structure is going to be, and then they can have variable sized arrays. This isn't really the case on Linux, where at best you have one structure that can be read in a single operation. Or at most two operations for things like sized for something like, I don't know, write V structures, IO vectors. But on Windows, yeah, reading data from user space can be a complex operation. And we found an example of this that could result in a privilege escalation on every version of Windows NT. The bug wasn't particularly exciting because you had to win a race condition to win it, to get code execution. So it wasn't particularly exciting for attackers simply because 9 times out of 10 you're going to get a bug check rather than code execution. But it was a legitimate issue, and it was a double free in NT filter token. So NT-filter token is the backend system surface that makes the Win32 API create restricted token work. How NT-filter token works would be that you'd pass it would pass a pointer to a helper routine that would try to capture all this complex SID data that it needed to pass. But we can force this to fail. But we can make a check pass that says the data is present because by starting the structure on a present page, and then saying it spans across a page boundary to a no access page. So we can cause some unusual error conditions like this, and by making this structure straddle a page boundary. So on error, this helper routine that was supposed to capture this user data would release this buffer that it was going to save the data into, and then return to NT-filter token. But NT-filter token didn't handle this correctly, and it would try to free the buffer again. So because there's only a short period between these two events, the kernel detects a double free and bug checks. So you only get one attempt to exploit this, and you need to get that buffer reallocated somewhere else within this very short period. So we know this is exploitable on MP systems because using a debugger we can let ourselves win the race condition every time. But in reality, nobody's going to be no real attackers are going to be interested in this bug simply because they'd only win 1 in 100 times. It was possible, and it was a fun bug, and there's a URL for some from example code that you can check if you're interested in how I did this. Okay, so this is another vulnerability in Windows NT. So this is a quote from Rusinovich in Windows Internal 4th edition. He explains that moving GDI from user mode to kernel mode has provided improved performance without any significant decrease in system stability or reliability. I think you might regret this quote. Maybe it's true, but there's no question that GDI represents a significant kernel attack surface now. And it's possibly the most easily accessible remotely. So it's obvious to us that font passing was going to be one of the weak points, simply because it's so easy to access via Internet Explorer's app font face support for CSS, which allows arbitrary web fonts to be downloaded for your web pages. This was probably our most critical discovery over the year that we were working on this, simply because just by visiting a website you could execute arbitrary ring0 code. This is interesting because it doesn't matter whether you're sandboxed or you're unprivileged or using protected mode. It makes no difference. We can exploit that and become the most privileged user on the system. It doesn't matter if you don't have administrative access or anything like that. It was easy to escape. So the way this worked was that the font format supported by Internet Explorer is called EOT, which is Embedded Open Type. It's essentially just a trivial DRM layer added on top of TTF format fonts. It defines some interesting data compression subformats called CTF and MTX. We actually also pwned these as well with some Ring3 vulnerabilities. These were, you can see MS10-001, but there's a couple of others that I don't remember the numbers. But EOT, is basically just added compression and reduced redundancy. CTF and MTX are actually quite clever data compression formats, and they're quite interesting to read. They do some cool tricks to make fonts as small as possible. I believe Microsoft licensed this technology from AGFA, and they published some documents on it. They're actually pretty cool if you're interested in data compression. Sorry. So, EOT adds some pretty silly extensions, things like support for XOR encryption and some other DRM techniques. The XOR encryption is really silly. It basically just, if the flag is set that says this is encrypted, it basically just XORs the entire data stream with the fixed byte 0x50. So, it's not particularly challenging to decrypt that. There's also some other another DRM technique called root strings. I think the idea is that if you have a font that you've licensed and you only want it to be accessible on your website, you'd put your website into you put all the URLs that you want this font to be accessible for into the EOT file, and then sign it. But the signature is ridiculous. It's basically just add all the character values and then XOR it with a fixed 32-bit D word. So it's not particularly challenging to defeat this. This is all handled by a library called T2embed. But basically, it just takes the EOT file, handles all the XOR decryption and so on, and then passes it to GDI. And then everything from that point on happens at ring0. So this is pretty scary. And it turns out we were able to find lots of integer errors when GDI passes the TTF directories. So the directories are basically at the start of a TTF file, and they explain where each table is in the rest of the file. This code was all executed at ring0, and the code was really old. It was unchanged since at least NT4. And in fact, if you go to ftp.microsoft.com, you can still download NT 3.1 service packs, and you can see kernels as old as like 94, 95. And the code is very similar. It's barely changed. So Microsoft wasn't alone. There were lots of other implementations that we tested that were vulnerable to pretty much the same bug. But it was mainly serious on Microsoft platforms simply because they run this code at such a high privilege level. So this was obviously exploitable remotely, but we only worked on a local exploit just for demonstration purposes. It was a very reliable and nice to exploit bug. Yeah, so this one was pretty fun.
We'll talk a bit about null pointer dereferences. So in general, what we call null pointer dereferences aren't necessarily null pointer dereferences. It's just in general two userland pointer dereferences, just when the kernel dereferences a pointer that goes to userland. And of course, if at any time the kernel trusts data in user space, there is a likely privilege escalation. So of course, the reason why most people call this null pointer dereferences is because null is a very common value. Because since it's a common initialization value for pointer, it's also a common error code returned as a pointer. And it's a special value in C. And so some people just expect it to be special to the underlying hardware, but it's absolutely not the case on x86. And very interestingly, they used to not be exploitable. So if you were familiar with Linux 2.0 and the versions before that, actually segmentation was used, and the kernel had its code base and its data segment base both above page offset, so basically above all userland data in code. So a different pointer without a segment override would never reach userland, which was quite convenient because I mean you explicitly had to write a segment override when you wanted to reach userland, so you couldn't unexpectedly reach userland, which was a cool feature. So wrong pointer dereferences didn't become to userland pointer dereferences automatically, and so their destination would be harder to control. Of course, you can argue that you still have some control over the kernel's address space from userland. So first, because there is this usually this hyperspace inside the kernel space that maps the physical memory, and also because, of course, indirectly you control some kernel structures, but still it would be way harder to control and to exploit those bugs in this situation. And interestingly, I remember that in 2004, 2005, we had some interesting threads with Linux kernel developers who did not understand the security consequences of them. And it was not really clear if they just expected null to be special to the underlying hardware, or if they still remember the more early days of Linux when this was not exploitable, but it was exploitable on other platforms. So I don't know what happened, but for some reason a lot of people didn't think this was an issue. And it was very surprising because it was one of the most trivial and easy to understand issues, but many people didn't get it. And so even recently, a few even senior kernel developers in Linux didn't understand that. We'll talk about mmap minadre later, because now this problem, I think, is very widely understood, and there is even a feature in the Linux kernel to try and prevent you to exploit this. So we found of course a couple of those types of bugs. One of those was the Linux kernel sock send page bug we found last August. It's quite well known, and actually it was nominated for a Pony Award yesterday because it affected all Linux kernels from 2.4 revisions and 2.6 revisions to date. So it was 10 years worth of Linux kernels, and every major distribution shipped vulnerable kernels. It was a null function pointer dereference, which makes it even easier to exploit. It was very, very, very easy to exploit. and we've seen public exploits for like a lot of architectures. So the way it works is the reason for this is every socket in the Linux kernel, every type of socket, has a set of functions, pointers associated with it called proto-ops, which stands for protocol operations. And those protocol operations, they implement the various operations that can be performed on a socket. So it can be accept, bind, shutdown, etc. And thanks to this, the general socket management code doesn't have to know about the underlying transport or protocol, because everything is abstracted away. So that's quite convenient, and you can see here the proto-ops definition as available in include/linux/net.h. So you see a struct proto-ops with different operations: release, bind, accept, and so basically what drivers do is they implement the operation they support, and they point to they implement the operation they support, and they point to operation they don't support to predefined kernel stubs. So in this illustration, you see, for instance, release points to my release, which is an implementation, bind to my bind, but accept points to sock no accept, which basically means this is an unimplemented operation. So this model is really fragile if you think about it, because anytime you add a new operations on sockets, what do you need to do? You need to update all drivers and point the new operation to a stub or implement it. And it's actually a lot of code to update, because it means all drivers, right? And on Linux, it's a lot of drivers. And also, since macros are used for initializations, you also need to update all those macros. So, of course, it went wrong. And when SockSendPage was added, so SockSendPage is quite old. I think it was added in Linux 2.2 actually. Well, anyway, so when SockSendPage was added, it assumed the corresponding proto-ops field will always be correctly initialized. And well, that was not a good assumption. So you can see here the code from SockSendPage, and if you read the very bottom line, it just returns sock-ops sendPage without checking that this is not null. So of course it went wrong, and it went very wrong because first a lot of drivers did not get properly updated. But the really funny thing that we found out was that the very sockops wrap macro, which is used to initialize a lot of drivers, had a bug. And the bug is quite subtle. I mean, if you want to take a look, it's not trivial to spot, I would say, because the macro itself uses a lot of other macros. It's a mess. So basically what happened is, for many drivers, even those which had been updated, sendPage was implicitly initialized to null. So, well, SockSendPage would happily start executing code at null for you. So the exploitation was just you map your shellcode at null, you trigger sendPage, for instance, by using the sendFile system call, and you get your code executed. So we wrote a trivial exploit for this that we shared with vendors, and but other people have written public exploits for like pretty much every popular architecture. So you can find this easily online. Shortly after that, we found another one, which was not as bad, but way more complicated. It was possible. We found out that it was possible to trigger a special code pass in UDP send message that would result in calling some function called IP append data with a null routing table. The interesting part of this bug is mostly that it's quite hard to spot. If you look at this function, the code path is really complicated. And this time it was a data null pointer dereference. The attacker would control some kernel data, a routing table, through address null, and this turned out to be exploitable as well, although it was less trivial. You want to talk about this one?
So another interesting Linux bug that we worked on was a use after free in the Linux f-async subsystem. So if a driver wants to provide asynchronous I/O notification, they have a linked list of f-async structs that contain the FDs and the corresponding file structures that they want to notify when I/O is available. The same file structure, it turns out the same file structure could be in multiple f-async struct lists, and there was a special one specifically for locked files. If the file was locked and then closed, there was a logical bug where the file structure would be removed from only the locked files linked list. The structure would be freed even though it appeared in multiple lists. So then you have this structure in the second list that's been released and is being passed out to anybody else who wants some k-malloc buffer. So the driver still had a reference to this freed file structure. So this was, we wrote a proof of concept, but we didn't get an exploit working simply because it was really, really complicated. But we released the information about it in Linux, and a guy called Gabriel Campana wrote an exploit for it. And he wrote an article in a French information security magazine called MISC, M-I-S-E. I don't read French, but I'm told from French speakers that it was actually an awesome article, so if you do read French, you should check it out. He used some really cool tricks to get it reliable and to make a reliable code execution. Yeah, you should check that out if you're interested.
So this bug is in NetBSD. It's the only NetBSD bug we are talking about today, but we really love this bug. Actually, investigating this bug took me more time than for a lot of other bugs we're talking about today. It was really nice. So we found out, well, I mean, it's documented in the Intel manuals, but it's not very easy to find, that an inter-privileged IRET can fail before the privilege switch occurs. So what we called this the commit point where the privilege switch occurs. So we said IRET can fail pre-commit. So for instance, if the restored EIP is past the code segment limit, a general protection fault will occur while in kernel mode. So no privilege switch will occur. So what difference does it make that no privilege switch occurs? Well, if no privilege switch occurs, no stack switch occurs between userland and kernel-land stacks. So basically you have no saved stack information on the trap frame. So if your operating system is not expecting this, and NetBSD was not expecting this to happen, so it was expecting a full trap frame all the time, well, basically you will have your trap frame shifted. So of course you can play with this and try to exploit this. And so we were thinking about this, and we also found out that the way the non-executable stack emulation work on NetBSD is they put a code segment limit just below the stack. So we found out that during a legitimate program's execution we could trigger the bug, because if you happen to have legitimate code on the stack, so that happens for instance if you have nested functions in GCC, you can get a trampoline on the stack. So if you're for instance in a signal handler in the kernel and you return from the signal handler to this trampoline on the stack for a nested function, you will directly return from kernel to code that's actually past the segment limit. So that's exactly the situation we described here. And so what this means is this bug can actually happen like this in real life and just crash NetBSD kernels. So we reported this a long time ago, I think more a year and a half ago, and I think it's still not corrected as far as we know. That one was really interesting because actually Tavis used this trick later for his NTVDM exploit, which I think you're going to talk about now.
Okay, so after we discovered these fun bugs in various interrupt handlers, we decided this was going to be some fruitful research, so we decided to audit the remaining interrupt handlers we could find. So we found one section of code in KI trap OD, which is the name of the GP trap handler in Microsoft public symbols. And we found one location where it appeared to trust the contents of the trap frame. This was a bit of a WTF moment for us, where we saw this code that was obviously doing something completely bizarre. We could tell that this was a component of the virtual 8286 mode monitor simply because the branch to reach this code was checking the VM flag in the eFlags image. So reaching this code was really hard work, and it took about 2 weeks of research to figure out how to start to reach this code. And on top of that, we needed to write a reliable exploit. But I think it was worth it. At the end, we found a really fascinating and ancient vulnerability in really the core of Windows NT. And yeah, I actually won a Pony Award for this last night, so I guess it was worth it. So this is a recap of some of the features that we needed to exploit this. If you can remember MS-DOS programming, you'll be familiar with int21, which is used to invoke system services. But if you wanted to make a BIOS call to interact with the hardware, then you needed to call other interrupt handlers. Most people remember int10 because it was used for things like the demo scene. So that one's quite famous. But obviously, you can't allow a protected mode task to interact with hardware this way. So in virtual 806 mode, these services are intercepted by the monitor. So Intel calls this concept sensitive instructions. So basically, what they do is any operation that a real mode program would expect to work is made sensitive, and that basically means that Intel will cause its GP and give the operating system a chance to fix this up or emulate it or do whatever it wants. So in this way, programs that could never be allowed to work in protected mode can all the services they expect to be able to use can be faked, and they can think they're working on a real MS-DOS system or whatever. So yeah, these actions trap, and then the kernel is given an opportunity to decide how it wants to proceed. So so the design of the virtual 806 mode monitor in Windows NT has really never changed since its implementation in the early 90s. And in fact, yeah, if you download these old service packs from ftp.microsoft.com for old, out-of-date versions that they don't support, you can still get a copy of these kernels. They even include public symbols, but obviously they're in DBG format, not PDB like we use nowadays. But still, you can still parse them and look around. It's kind of archaeology for code, I guess. It's kind of fun. So yeah, in order to support these BIOS service routines, a stub exists in the GP trap handler that restores execution context for the trap frame. In order to access this code, it's authenticated, but these were by magic values that we already knew that we could forge from our VMware exploit and from our previous work on interrupt handlers. So we knew that we were onto something that we could really control. There were lots of hurdles on the way, and it took us a long time to reach this. But each one was an interesting exercise, and I'm going to talk a bit about them. So how do you interact with the virtual 806 mode monitor? On Windows NT, it's an undocumented system service called NT-VDM control. It's authenticated. You're not allowed to access it unless you have a special flag in your eProcess structure called VDM allowed. You can't set this flag unless you have SE TCP privilege, and you'll use something like, I think it's NT set system information or set process information, and you need SE TCP privilege. So if you have SE TCP privilege, like TCP is trusted code base, then you're already one of the most privileged processes on the system, and you don't really need to escalate privileges any further. So it's not immediately obvious that you can still access this system call. But you can defeat this really easily. All you have to do is invoke the real NT-VDM subsystem, and then use the Win32 API, create remote thread to execute within it. This way, your thread is executing within a process that already has this flag set in its eProcess structure. So yeah, NT-VDM control is completely undocumented. The best documentation for it is really Alex Ionescu has already reverse engineered it, so you can work out the API from his code in React OS. So yeah, he's already done all the hard work, so you can understand it that way. There's still a lot of special cases that we needed to understand for this particular bug. We needed to bypass things like checks for structure sizes and magic checks and so on. It took some time. But yeah, Alex Ionescu's code in React OS was really how to understand this stuff. So this code that we'd found in the GP trap handler was guided by a test for a specific CS EIP pair. We can forge these with these trap frames by making iRetTrail, but you can't request to return into an RG code segment. Obviously, that would be stupid because you're just using an RPL0 value, and then you'd get instant kernel code execution. So nobody would be silly enough to make that mistake. But as we already know, CS loses its magic value in virtual 86 mode because you need to be able to access these this 20-bit real address space. So it's completely reasonable to request any value. But we still need to cause iret to GP. And we did this by setting the TF flag in the E flags image when returning. So Intel actually considers this sensitive and hardens control over the virtual 8086 mode monitor. But this is actually poorly documented. And in fact, there's no mention of this at all in the documentation. And from research, we know that early versions of the Pentium processor would in fact not treat E flags, TF set in the E flags image as sensitive. And that wasn't considered sensitive at all. But apparently, during some later revisions of the Pentium, Intel updated this and did consider it sensitive. And in fact, this is really documented by, I don't remember his name, the Sandpile. Yeah, so there's this great resource online called Sandpile where lots of crazy Intel tricks are documented. And yeah, so it's explained that at some point Intel decided that this should be sensitive and they updated it, but they never issued any errata or they never updated any documentation. So what we think might have happened was that Microsoft, during this, when Microsoft implemented this, they believed that they could rely on this, and then Intel suddenly changed the x86 document specification so that it was sensitive, and Microsoft never bothered to check whether these checks were still valid, which is pretty reasonable. I mean, how many people check this low-level code every day? It's the kind of thing that you write once and nobody remembers how it works. Just don't touch it. So yeah, so we found that by experimentation we proved that this is actually still the case. So I have a video of this. It's not particularly exciting to watch, but it's. Okay, so yeah, so I wrote a reliable exploit for every supported version of Windows NT. You basically just invoked a new process and it would hand it over a system token. So yeah, it was very reliable and it worked perfectly. And in fact, it was a bit of a challenge to write because all the existing published shellcode for Windows NT privilege escalation bugs were never expected anything to work across more than one or two kernel versions. So everything published was like very Windows XP specific or whatever, and they had like hard-coded offsets into structures and so on. And so yeah, I spent some time working on a completely kernel-neutral version that would work on every version of Windows NT, simply because there wasn't an exploit no exploit existed like this around that I could reference. So I have some code that I can show you. So what I did was, so this is where where the kernel lands after I exploit this vulnerability. And so basically I have to start writing a driver code as if I was writing a real driver based on like, symbols that Microsoft supports, so that I could be sure that they would be available on every kernel version. So yeah, I basically have to work out where my kernel is loaded and then start parsing the kernel exploit directory myself manually. So then I can basically write driver code as if I was writing a genuine driver. So because the kernel stack gets desynchronized because I'm passing it this fake stack that I wanted it to swap to, it turns out that my whole K-thread structure gets completely messed up. And in order for this corruption to propagate to other parts of the system, I have to repair it. So I find all references to this fake stack I've set up and restore them. Because I'm going to kill this process anyway, because I only want it to use it to paste a privilege token onto another process. I don't really care what it points at. I just want it not to be corrupt anything. So yeah, so basically, yeah, I search for all these values. Then I find the most privileged process on the system, which is the initial system process. Grab a reference to its primary token and then paste it onto my token. Paste it onto this process that's unprivileged. And yeah, and this works on. This only uses exported symbols that Microsoft support for driver developers. So it's completely reliable across every NT version that was affected. So let's see. So basically, I set up this kernel stack, and the offsets for things like restoring the TEB and the new stack pointer, which is going to be a fake stack in the user address space, and change the return address into my exploit. My payload. So you need, in order to access this code, you need a data structure called a tib in your tab. I don't know what TIB stands for. I guess it's thread information block or something like that. But TEB is obviously thread environment block. Then you initialize the VDM subsystem, and it turns out because this data structure is unsupported and undocumented, Microsoft don't mind changing it as much as they like, which is obviously completely reasonable. But in order to identify which version is being used, there's a size field, which if it isn't the correct value, they say they return access denied. But because I don't know what the size should be, because in fact it even changes between service packs, so I can't even guess from the version. So I just basically have to brute force it and try every value until it works, and this works fine. So yeah, because the real address virtual 806 mode, Intel expects you to map the virtual the fake real mode address space on the first page. You need to map null the first page. So there's no documented way to do this, and in fact, if you try to do it with any of the Win32 APIs, it just doesn't work because null has special meaning, and it means you have no preference to whether this is going to be mapped. But if you use NT allocate virtual memory, which is the system call that backs all the stuff that all the regular allocation stuff like virtual alloc and so on, then it's possible to do that because it rounds down addresses to the nearest page. So if you wanted something mapped at 1, the address 1, then obviously 1 isn't a page boundary. So if you want something mapped at 1, the only way to do it is map something at the next available page, which is 0. So yeah, you basically just pass in a really low address, it rounds it down to the nearest page, and you get it mapped. And there you go, and that works. So we've also been working on automation and fuzzing for operating system kernels. So we've been working on system call exploration to try and find interesting attack surface that we want to reach. On Windows, the system call interface, it's complex, it's unstable, it's unsupported, and it's undocumented, and it's also pretty vast. If you consider Linux has about 300 system calls, Windows actually has about 1,400. But in fact, that's a pretty conservative value because Microsoft really liked this design of multiplexing system calls. On Linux, there's only one multiplexing system call, which is socket call. So things like bind, accept, and send, and things like this are all the same system call called socket call, and you just pass a value saying which one you wanted. But Microsoft love this, and they have dozens and dozens of them. So you pass a magic value which tells them which system call you actually wanted, and it can be dozens available via one entry point. So in fact, 1,400 is probably a pretty conservative value. There's basically 1,400 SSDT entries, but there's more likely, I would guess, about 3,000 system calls really. So on Windows, these are designed only to only ever be called by Microsoft code. They make it very difficult to call system calls, and they're not supported across versions. So they don't mind breaking stuff, which is perfectly reasonable. This is all expected. As most people know, I guess they randomize system calls for system call numbers between service packs just to make sure that you're not trying to rely on this. Well, I guess that's probably not what it's designed to do. They just do that as part of the build process, but that's the effect. Because no Windows programmers call these system calls directly, they only go through the Win32 supported and documented APIs. They're rarely exposed to malformed parameters. So in general, simple fuzzing can still expose interesting bugs, simply because real-world programmers aren't touching this stuff. So yeah, on Linux, if it's expected that just regular programmers will call system calls, and in fact, when new system call functionality is added to Linux, it's quite common to see regular programmers post bugs or reports that an oops has been caused as they try out the new code. And this weeds out lots of bugs before it reaches anything that could be security sensitive in like enterprise distributions or whatever. But yeah, this isn't the case on Windows simply because this isn't designed to be called by end users. But obviously there's nothing stopping you to actually do that if you're an attacker. So also the design of system calls on Windows NT is very different from the philosophy on Linux. In general, on Linux, structures are very simple. They can be read in 1 or 2 operations, and they're easy to pass. They're very simple structures, but on Windows, they're often complex objects. They're multiple levels deep. They have large interdependencies that all need to be passed. If you set pathological parameters in these complex structures, you can reach some very rarely exercised code. And in fact, there's code that you just simply cannot reach via any supported interface, and it's difficult to imagine how Microsoft managed to test this. And no end users are going to complain simply because they'd never rely on this code. Of course, kernels also pass lots of interesting stuff like fonts and other complex formats, and this is all done at ring0, and these are great fuzz candidates. So we've been working on system call fuzzing. So trivial fuzzing can still find Windows bugs. The attack surface is really large, and there's lots of system calls to play with. You can find fuzzing on Linux, but in general the task is not so trivial simply because the interfaces are so simple. It's tough to get them wrong. You need to do some work. You need to set up some I don't know, complex state with file descriptors or whatever. But fuzzing will find bugs, and we've had some success this way. We've been developing some techniques for working on this that we're trying to integrate into things like Chrome OS release. So we're hoping that this can help make things like Linux privilege escalation via malformed system call operations easier to spot as they're introduced via regression testing and so on. So we're hoping this is going to help Linux local security in future. So yeah, now we're going to talk about protecting the kernel from malicious LAN code.
One of the first ways that was quite popular to try and protect the kernel from malicious user-land code was just having trusted path executables. So, well, I mean, the idea is just to have trusted executables only. So it's reasonably old. I think I've seen this. I've seen people running shell boxes in the mid-90s using this. So it was pretty popular, and there was a very naive way of doing it on Linux, which was to just mount all use of writable paths to no exec. So if you could write somewhere, you could not execute the code. There were trivial bypass for this. For instance, for systems which already supported dynamic libraries, at the time, you could just go through the dynamic loader, because the dynamic loader LD would be in a trusted path, and it would happily map your code. It's a job, and execute your code. GRSecurity had a good GID UID based one for years. I think it was released in 2000 or something like this. And nowadays, it would actually work if you, well, it could almost work if you would just mount something with no exec, because nowadays the semantic is actually respected, and it does prevent file mapping as protexec and not only execve. So this approach is gaining some popularity on the Windows platform through whitelisting. We've seen a few products that try and perform whitelisting on the Windows platform. So the idea is just to prevent gaining arbitrary code execution in the first place, so that you can't attack the kernel. But of course, there are tons of ways to bypass this, because arbitrary code execution should not only mean arbitrary opcodes. You can exploit lots of kernel bugs from a Python or a Ruby interpreter. So if Python or Ruby are in your trusted path, you can just exploit kernel bugs through this. Also, if you think about powerful executables such as GDB, you can do whatever you want through GDB. So if you have access to GDB, you can obviously run arbitrary code. Also, quite interesting tweak if you're trying to build a system with trusted path executable, the threat model is completely changed for many binaries. For instance, a local vulnerability in NetHack or the Minesweeper on Windows would become useful, because they would allow you to run arbitrary code. And you've probably seen a few releases, such as vulnerabilities in make or vulnerability in ZSH, which didn't really make any sense. But in this very paradigm, they do make sense. So of course, this is also useless if the attacker already has arbitrary code execution. So if you're trying to protect a browser sandbox with this, it's useless because you're assuming the attacker already has arbitrary code execution in your sandbox. Same thing for OpenSSH or VSFTPD privilege separated sandbox. So what could we really do that would be useful to do proper sandboxing and attack surface reduction for the kernel? Ideally, a process could opt out from some kernel features it does not require. On Linux, there is nothing really that allows you to drop privileges in a discretionary way. And all the focus is on mandatory access control on Linux. And basically, the paradigm is very different. If you're a programmer, what you want is, you know that you know your program, you know how it works. So you want to be able to define a policy for your own program. But mandatory access control is more about an administrator on the system being able to define a policy. So if you're writing a web browser, it's not what you want. On Windows, there are slightly more privilege dropping-like features, thanks to the control over token, and more recently, since Windows Vista, we have things like integrity levels. So there are some privilege dropping-like features, but there is still nothing to protect the kernel's attack surface. So the options are limited. And on Linux, for Google Chrome, we needed something like this, and we did some hacks, and we have a SetUID sandbox design that you can look at if you're interested in this. We've published slides at Blackhat Europe about this, and it's quite weird because nothing was really designed for this, so we kind of hacked our way through it. Also, ptrace-based sandboxes are quite popular. The idea is to use ptrace to be notified whenever an untrusted process will perform a system call. So this can be a good choice. Unfortunately, of course, it's slow, but otherwise for security it can be a good choice. But it's very hard to get right because ptrace was not designed for this at all. Also, on Linux there's one feature which could have been interesting for this, called seccomp. Seccomp is a special mode you can switch your process into that will only allow the process to reach 4 system calls. It will allow the process to reach read, write, and just exit, plus sig return to be able to handle signals. So it's just those 4 system calls. So of course, the kernel's attack surface is incredibly reduced through this. But the problem is, for instance, for Chrome, we were very limited. 4 system calls are not going to be enough. We need to be able to allocate memory, for instance. And one Googler, Marcus Gutschke, is working on a seccomp-based sandbox, and he's using crazy tricks such as sharing address space between different processes, sharing file descriptors, and then other processes which are not under seccomp are able to proxy the needed system calls. It sort of works, but it's not deployed into Chrome yet. But you can already look at it. So another popular alternative is basically people say, okay, we can't protect the kernel from malicious code, so what can we do? Well, let's reduce the kernel's privileges by using virtualization. So lots of people do this. Of course, virtualization has its problem and also expose quite a lot of attack surface nowadays, especially in some popular products. So, well, it's a good idea, but of course it has its drawbacks. Something else to protect the kernel is UDREF. And as we've mentioned, unexpected two-user-long pointer references are an issue. And I've mentioned before that on Linux, they used to not be exploitable because of thanks to segmentation. And so the idea behind UDRF is very simple. It's just to make the kernel segment, the kernel's data segment descriptor expand down and put its limit above user-learned code. The problem is, what can you do on 64-bit systems, since for most of it, segmentation is not there anymore. So you can always do full address space switching or other small tricks, but it's going to have some performance penalty. So mmap min-array was a pragmatic attempt by the Linux developers to tackle this problem in a portable manner. The idea is just to have a system-wide minimum address that can be used in a process. Usually it's set to 64K, so user-learned processes cannot map behind 64K. But there is an exception, of course, for processes with the capsys row IO capability. So lots of root processes, for instance. This has been plagued with many bugs in the past. It's in much better shape now, but we found one bypass that we'll present now, and we found another one that we need to investigate. So we use personalities. The System 5 Release 4 operating system maps page 0 as read-only. And so unfortunately some programs depend on the behavior. And to make porting programs easier from System 5 Release 4 to Linux supports a System 5 Release 4 personality. So this personality is per process, and it's kept on execv, of course. So the funny thing is, we could get this personality and just choose to execute a setuid binary. And then, since this is a setuid binary, it automatically gets the capsys for IO capability, since it executes as root. And thanks to this capability, the mmap min-array check is bypassed, and a page is mapped as 0 in the address space. But of course, there's not much we can do. It's a root process we don't control, which has a page mapped at 0. So yeah, you could imagine that if this root process, process has a vulnerability like a null pointer reference, maybe you could exploit it. But we were trying to actually regain control of this process, and so we started to look for a binary that would drop privileges and let us regain control without going through execv. And we actually found one. PulseAudio allowed us to do this. And it was not a bug in PulseAudio, it was just a bug in the Linux kernel that we exploited through PulseAudio. But then, of course, then we discovered PulseAudio, and we took a look at it, and of course we also found a vulnerability, a completely different vulnerability in PulseAudio that was unrelated. So yeah, other kernel protections. Well, there are a few kernel protections from PAX, but we don't have much time now if we want to take questions, so I will go through this quickly. So there are lots of bugs to find in kernels. We found 20 of them in a year, and we were still doing a lot of other work. So there are lots of bugs to find. The attack surface is growing in general. And the really interesting thing that's not necessarily expected is it's actually easier to reach this attack surface from remote. If you've attended our talk on virtualization at PACSEC, we've also said a similar thing for virtualization, because basically what happens is, for performance reasons, people want to design systems so that everything goes through as fast as possible to the hardware, and there is actually more and more low-level attack surface exposed remotely, which might be unexpected. And so the exploitation of those flows goes from very easy to very challenging. It can be really trivial and really hard. It's really hard to also get rid of the kernel's attack surface. Even in systems designed with security in mind, it remains. So yeah, we're hoping that Microsoft will have some kernel's attack surface reduction facilities soon in Windows. We'll see how it goes. Also, you can really say that user-learned exploitation prevention is kind of mature, but in terms of Kernel exploitation prevention, it's really at its beginning. And all the current sandboxing techniques you see in Google Chrome, now in Microsoft Office, soon in other products, really make the kernel an ideal target. So thank you for attending, and if you have any question, we can take them. We still have 6 minutes. No questions? Thank you. Bye.